subject, many to get inspired by many phenomena in nature, and also to provide some hints for the other courses that you will attend during these 2 weeks. So for that reason I call statistical physics tales. As I said, I have no pretensions to any completeness in this lecture. So the rule is just enjoy it and get just inspiration from what we saw under our eyes. So probably the things that you have never realized is how to check if a system is an element as a spin or not. So the first is nitrogen put within a gradient of magnetic field and nothing happens. But when you put oxygen, for instance, immediately you see that it sticks between the magnets, and this is indeed the phenomenological manifestation that the oxygen is a different nature of nitrogen and a spin. Okay, so we couple just to the magnetic field as well. Other things which one has to realize in this subject is the idea that any system, especially macroscopic system, has a ground state, which might be extremely complicated or might be simple, depending, and this might vary according to external nodes. So for instance, take these elements at ordinary temperature, nothing happens, as you have seen before, but when you pull it down, then something is going on. Okay? So the nature of the ground state has completely changed, and therefore the response of the system to some probe has provide a non-trivial answer. Now, the question of understanding and characterize ground state and excitation above it is one of the main questions of the subject. Okay? So as I said, you might have to face complicated ground state, but what is interesting that sometimes you do not really need to understand the ground state, but the excitation above it. Okay, so another way of probing nature, as you probably know, especially nowadays, is to reach very low temperature. Now, temperature is a concept related, as you know, to motion, and this is, has been made possible to reach incredible low temperature using laser. Laser simply because when you shoot laser on atoms and you put them in a magnetic trap, in an optical trap, what's happening is that the atom cannot move any longer in any of the three directions, and therefore the only things he can do is just pull down. Now with this technique, nowadays one can really explore new phases of matter. Organizers.
Okay.
Okay, so all this is really a window on the quantum world and all the amazing law that we learn, but we have to explore really on a macroscopic scale. So what are we going to talk today? So I'm showing you some really simple phenomenology of phase transition and some main ideas which are behind the study of this subject. Then I will discuss the key core idea of an organization group, which are behind the comprehension of many of these phenomena, the role of quantum field theory, describing it, and some statistical models, and concluding, say, with the embarrassment of the rich, in the sense that we'll see that really nature has astronomical richness in its variety, and not only coming from, say, from the physics, but also from mathematics, for your abstract questions as well. So let me start really something which we have under our eyes each day, water. Now water can be in a liquid phase as well as in a solid phase, and solid also in a beautiful pattern, beautiful form. And you know, this snow crystal has highly sophisticated structure as well as bubble. So what I'll show you in really in a snapshot is what you condensate in a diagram that, by the way, was Irish chemistry in the 18th century, Andrews, the first that understood that when you put pressure versus temperature in any elements, there is a critical point which separated the liquid with the gas. This make reasons of something that people like Faraday or other observed that time, namely that exist gases that no matter how they push it, they never become liquid. But the reason was that the experimentalists were working at temperature above the critical one, and therefore no matter how you push the gases, no matter how pressure you put on it, you never get a menisque between the two. You never have a separation between gas and liquid. Okay? So to observe this, you have to work above the critical temperature, and therefore there is this phase diagram which is like this. Now you probably know as well that if you take a gas, you take the ideal gas law, you never can describe such phenomena. And the reason is that the ideal gas that satisfies P times V equal RT as a system without no scale. There is no scale, you assume the atom is pointless, and therefore you can prove it, actually prove it, that the internal energy of such system with no scale is a very simple form, depending on the temperature, and nothing can happen with that. So to get really from ideal to reality, you have to introduce scales. And this was the job done by Van der Waals. That with a very simple idea, which nowadays we know what it is just a virial expansion of the partition function, it just got a law, which is here, where it introduced two corrections. The first, which has to do with the volume of the particle, so scale, by another scale, come from the fact that atoms, molecule, has felt the attraction by others. And actually you can extract this number very easily from the experiment, relatively easy. You can work really on range which are not nearby the transition point, and then here they are plotted, some numbers. Now we'll show you in the next slide that the critical temperature where something happens, where the gas becomes liquid, essentially depends very much on this attraction parameter A, which is a measure of the forces. And now observe how this parameter becomes smaller and smaller and smaller when you go to hydrogen and helium. And not surprising, that were the gases that were liquefied in, after a long effort and after many efforts by experimentalists. Indeed, when you go and extract all the parameters of your system, now is a cubic curve, the one which rules pressure and volume. Therefore, there is one point where you have really zero derivative and zero second derivative. So this defines the critical values. And observe that the volume depends on B, which actually is the B. As a matter of fact, the cubic root of B is just how large the atoms are. While observe that the critical temperature depends from A and B, and it's clearly A. So this is the reason why, if you read really article, or if you want, if you read the history of physics, when you read things like you know that hydrogen should be liquefied around -100 centigrade, you say, how the hell he knew it? He was not magician. I mean, how he felt that has to be there? Simply because he estimated these parameters, and from there you can have an idea what the critical temperature is. Okay? And therefore, you see immediately that hydrogen has to be liquefied very, very close to zero, as much as the helium much farther. Okay? Now, what I want to say, apart the fascination of this story, which is not the main topic me today, is one thing which is very general. The very general thing is that when you have critical phenomena, as it is the one I'm discussing, exist quantities which are not at all universal. For instance, the value of A, B, so on changes. As well as changes, accordingly, we see the critical volume, the pressure, critical, the temperature, and so on. So these are microscopic parameters which depend very much if you change the elements and change accordingly. However, this is the important point, if you choose a right variable, in particular a dimensional one, immediately you get something which start to have a universal form. So completely somehow independent of which element you are talking about. Okay? So van der Waals equation assumes this universal form where all the dimension full parameters is gone. And actually you can have a very interesting check of this law, just measuring what is this ratio, Pp over RT, for many, many gases at different temperature. You observe that they always collapse on a universal curve. Okay? So this is called universality. So, namely, if you take a system which falls within, modern terminology is within the same universality classes, you might change critical parameter, you might change the dimension full parameter that this system has, but as far as you report to universal form, they fall down in a unique curve. Now, the van der Waals is, you probably know, an example of first order phase transition. However, in nature, we are mostly interested in second order phase transition. And this concerns typically models which come from magnetism, for instance, okay? Where you have degrees of freedom, where typically you model in terms of spin living on a site, and then interacting according to some law, which the most interesting one is when they are next neighborhood. Why that? Because you want to have as much as is possible locality. And out of locality you can nevertheless take long range phenomena interaction. Okay? So then, as I said, you might have magnetic material of different type. You might have interesting what nowadays is called spin liquid or quantum liquids, and are peculiar states of matter subject to law simultaneous quantum mechanics, but also statistical physics as well. And to study all that is crucial that we appeal to this guy. Who is he? It's probably a name that each day you come across. No. Okay. This professor, easy, I would say. Easy. Because he was German. He was Jewish, German. Okay? Now, a name that is probably the most famous in physics, although the other is the less unknown. Okay? So, Ising, you know, had the PhD argument by Lenz to study a simple model plus and minus, And what he did is discover that in one dimension there is no phase transition. This was enough for him to provide immortality. So, we know what this thing is. It's just a spin which can get black or blue and red, subject to local interaction. And depending on you vary temperature, here on varying temperature, the system can magnetize, have a macroscopic configuration or not. So we are changing our parameter, it's changing the ground state of the system. So phase transition in a nutshell is essentially a competition between order and disorder, and everything is ruled, as you know, by the free energy. And free energy is made of two terms. The first one is energy, and the second one is entropy. And what is the term which makes them competing? Is temperature. Okay? So, you might have other parameters, obviously, because internal energy might depend also on pressure, might depend on other things, magnetic field and so on. But essentially, there is a parameter which immediately install a competition between the tendency of the system to order, to minimize energy, and the term which likes to be as much as disorder it can. And the two are balanced by temperature. So for that reason, we observe in nature many, many phenomena, starting from the temperature of the sun. How much is it? How much?
5,000 Kelvin.
Then you start decreasing, you arrive to ordinary temperature, but then you can cool down, according to technique that I have no time to describe you how to reach it. But at the end of the day, we arrived, at least at the beginning of the 19th century, around 4 degrees by the liquid, by making the helium liquid. Who did it? Who? Mussardo. Mussardo was a theoretician. Like Pauli, if he went to lab, everything blows up. Honest. Okay? So it was the first to liquefy helium. And you probably know that 3 degrees is on the other end the temperature of universe. Okay, the cosmic radiation. So, microscopic system, why temperature is also important? Because in macroscopic system, this chair, this table, ourselves, is made of milliard of levels. It's like the barcode of the supermarket. Okay? So if you look at it, you have millions of these levels that just pack one on top of the other. And these energy levels can be probed essentially in terms of another scale which is provided by temperature. So temperature is just like a lens which allows us to enter into the structure of material. So as far as we are relatively large with respect to the energy gap, essentially the energy looks to us continuous. And we can apply law which come from the ordinary classical mechanics, Dulong-Petit law in specific heat of material and so on. However, when we start looking on a smaller and smaller scale, alias, when we go on temperature which are much below or comparable to the energy gap, well, at this point we start feeling what's going on the quantum level. So, moving with temperature, we really probe material, and therefore we start observing macroscopic phenomena, the ones at the beginning were superconductivity, but then you might have also the corresponding condensation of excitation, which are superfluidity, is in helium, that are just under your eyes gigantic macroscopic wave functions. Okay? So what you observe is a macroscopic gigantic wave function, and the result is that this system has certain rigidity in moving the ground state, this gap, which protect it, and then provide many phenomena like the superfluidity, no friction, fountain, and so on and so forth. Okay, so this is give us a glimpse, I would say, how beauty is the nature in many respects. Obviously, I just picked a few examples. You can take your own. There are many other fascinating examples. However, not only we have to watch, not only we have to appreciate, but we have to understand. And understanding might be done according to a general statement that Paul Dirac made and used as a guideline of his career, alias physical laws must possess mathematical beauty. So can we understand all so different phenomena, many different, magnetism, water, superfluidity, and so on and so forth, according to some really beautiful and unified principle? So this is the challenge. The challenge is to understand in a unique way, in an economic way, something which appear very diverse and very different. Well, amazingly enough, all this can be reached according to two basic principles. One is symmetry, and the other one is universality. So these two principles essentially are everything you need to package all the physical property of systems. Okay? So just two basic principles. Now symmetry means that you have to look at a certain model, and with certain ingenuity, with certain smartness, with certain intuition, you have to understand what is the parameter that might characterize the different phases of matter power. Phases are just thermodynamic states of matter that, if you move around, remain the same. Okay? So this is what is called order parameters. Requires certain ingenuity, as I said. You might feel, smell that this probably there is a Z2 symmetry, the simplest group, or might be extraordinarily complicated. Might have ON, SUN, other. You just take the table of group theory and you choose your preferred group. Might exist in nature, something like that. In any case, symmetry just tell you what are the order parameter and under which representation, this is the text of the word, it transform accordingly a group of symmetry. Now, once you have this, symmetry fix for you the way of writing interaction among the ordered parameters. Okay? So imagine I told you that something relevant to understand certain phenomena is a vector, is ON vector. And imagine that I told you that everything should not really depend how these spins are oriented. How can be the interaction between the spins? What are the quantity out of spin which doesn't change if you change the rotation on which the way you are looking at? Eh? Scalar product. Okay? So, what you have done in a nutshell is construct an invariant under the group. Okay? So, when you spot the group symmetry, you spot the order parameter, automatically you are selecting way of writing interaction between the order parameter which is invariant under the group. So, imagine you have Z2, the simplest one. You have an object which is a scalar function phi. What is the quantity that you can construct which is Z2 invariant? The only one? Eh?
The absolute value.
Boys.
The absolute value.
Okay. More. Eh? Any even function. Okay? Any even power. X squared, x4. If you want modulus, absolute, but modulus violates something which a priori is not obvious, which is analyticity. Okay? So this is another requirement, especially pointed out by Landau and Ginsburg, that you should have somehow certain analyticity property behind it. Why is another story. But modulus has the unpleasant feature to have cusp. While if you have x squared, x4, x6, and so on. So once you spot a symmetry, automatically you spot the order parameters, automatically you have a way of selecting class of interactions. Now imagine that you have a Z3 symmetry. Now if you have a Z3 symmetry, you might know, and if you don't, you have to go and look Landau, for instance, that the simplest representation of Z3 are doublet. Okay? So you need at least two fields which are complex conjugate one of the other. Okay? This is simple. Unfortunately here we are handicapped between a blackboard and there is no.
Not yet.
Okay, but think about how to construct where. I don't know if they can look at. Can you see here? Okay, so we were saying that if we have, imagine that, so there is a certain, as I said, ingenuity, a certain work behind it. Imagine that you have spot or you have a suspect that your material is invariant under Z2. Now, in group theory, given any group, there is a certain number of representations which are irreducible along the group. Now, the theory of representation is something which you learn on books, is not arbitrary. Okay? So, for instance, for certain group, you might have dimension. Representation means linear space on which you represent all the operation of the group. The dimension of the matrices is fixed. Is given. So for certain groups, for instance, you might not have a three-dimensional space for representing your group accordingly. Okay? So for Z2, which is the simplest, the representation are one-dimensional. So you have order parameters, which might depend on point on your system, that you call phi x, and then you have to write down certain measure for the fluctuation that this system might have. But then you have to do accordingly to the group of symmetry that might be behind. Now, there will be certain non-local terms, which I will forget for minutes, but then there will be certain potential terms. This potential term will be made of terms which are explicitly invariant under the group and terms, you can classify them, that explicitly break the symmetry in this case. So for Z2, we saw that the most general potential which is invariant, this is a function which is invariant under this Z2 operation. So any even function. And accordingly, the one which breaks the Z2 is any function which is odd under this x. Okay? So simplest example is what we know. The simplest example is the one which is a term like this. Then you might complicate the life and put something which is quadratic. You might complicate further the life and then you put something which is cubic and so on and so forth. And the simplest example of this, on the other hand, is something which is linear in the field itself. Okay? So, depending which term you put, accordingly you define different classes of universal. So this is simple, this is what we learn from the first day school and so on and so forth. Now, a less trivial exercise is, on the other hand, if I told you that the group of symmetry is Z3, or better, Z3 cross Z2, which is essentially what is called the diedral group tree. Okay? Open Landau, Landau tree, everything is there. So this object now is not abelian any longer, and you have to look for representations. Now representations, as you know, are constrained in dimension by the so-called Barn-Side theorem. Everything is in Landau. So you realize that apart the one-dimensional representation, which is trivial, the less trivial representation in this case is two-dimensional. So you should have an object, let's say called psi, which has to be adapted. Okay? So what is Z3? Well, Z3 is essentially the group of symmetry which are behind the cubic root of identity. Okay? So all these imply that you have order parameters which has to be independent how I measure it as far as I change the angle to pi over 2. And now let us constrain the most general potential that I can construct accordingly to this psi. This means that this object, let me say that this has to be invariant under arbitrary rotation. You see, I should have, with a two-dimensional guy, I can introduce complex something. Okay. So I shall have an order parameter which is complex, and all my potential should be invariant if I change psi rotating 2 pi I over 3, and power of course, but this is the simplest one, and psi bar minus 2 pi I over 3. So what is the most general function which are invariant under this properties?
Function of the product.
So the first thing is this guy has to call, let's call y. Is correct? Is the only one?
Any of these to the power 3, so your psi bar is invariant.
Sorry?
Any of these to the power 3.
Precisely, so I can add this. imagine now that you have the charge conjugation. This Z2 is charge conjugation, is the one which swap sign with sign bar. Do I have constraint on these things?
F and G must be the same.
Yeah. Okay. So you see how powerful the group, the symmetry is. Now, accordingly then you expand in power. This is the Landau-Ginzburg approach, to expand a complicated function then in power. And the most general expansion of the power defines the different universalities. Okay? So this is in a nutshell the things. And now let's go back okay, so let me go back to what I was saying before. So the great advance that has been made after many decades of studies is that to understand a huge variety of phenomena in nature, you have to rely on these two things. So symmetry, I told you what it is. So you have to spot what are the transformations which leave your system invariant. The second one is universality. Now I have to tell you what universality is. So this is at the basis of the renormalization group analysis that was pushed by many people, Kadanoff and in particular Ken Wilson. So what is the idea? The idea is the following. Given a system, there is essentially always some microscopic scale that you can identify. Okay? So this say you are always look at system with certain lengths. And any system has certain scale. So for instance, in this room, the obvious scale is order meter. So is the distance between two of you. Okay? At least with my eyes, what I'm looking at you from these distances. So the idea is you look at a system, you identify a certain microscopic scale. For simplicity, I take a square, just for sake of clarity. And then at that scale, and this is A, you write down certain Hamiltonian density. This encodes the information we have about the interaction between the elements at that scale. And the crucial idea is that you can write down this Hamiltonian in terms of spatial operators that at the end of the day will be called scaling operators with certain coupling constant. Okay? So I repeat it. So you take a system, identify a scale, and on that scale you write down the interaction, but you write down in a smart way in terms of monomial of the fields, therefore has to respect all the symmetry that we discussed before, but they are also spatial in a way I'm telling you in a minute, and with certain coupling constant before. So why these are spatial, these fields, and how to identify them? Because the key idea is what's going on if you look the system varying the scale. What happens if I start looking at you, just moving far away from it? Okay? At this point, I would like to understand how changing the scale, how the Hamiltonian change. Well, if you have identified the proper scaling operator, the transformation is very simple. Obviously, this is only definitive, goes without saying, but conceptually, if you have identified a scaling operator, changing the cutoff, as is said, the field scale just multiplicatively. So say differently, these objects are eigenvector of the scaling transformation. Now, if you have written down the most general form of the Hamiltonian, which is invariant under the group, so for instance, the function I wrote you before, is the most general. When you do this transformation, and you are changing just the coupling constant in front, you remain in the same functional space. Okay? So if you have written down the most general Z2 Hamiltonian, rechange the things, you remain Z2. So all this transformation is just a map of Hamiltonian into a new Hamiltonian in the same space. Therefore, you add what is called renormalization in the coupling constant space. So you identify the symmetry and you write down the most general monomial which are invariant under the group. Now, at a given scale, you fix their value. So, for instance, Z2 symmetry might say, at the scale of 1 Armstrong, I just have phi square and phi 4. But then the question is, what happens if I change the scale? Well, other term will be produced by this transformation. And you get what is called effective action, effective Hamiltonian, which tell you on a different scale how the order parameters are interacting. So you can see this as a flow in the coupling constant space, and this flow takes the mathematical look of dynamical system. So it's like what is mathematically is called dynamical system, so a set of variables which are updated according to some nonlinear rules. Now the magic is that, on the contrary of dynamical system that you might study abstractly in mathematics, where the behavior will be extremely complicated, in this case physics rule differently the story. So for instance, this flow can only cross in spatial points which are called critical points. What are critical points? Are the spatial value of the coupling where no matter how you change the scale, the value remains the same. Okay? And they can move on from the fixed point. When you perturb this fixed point, they can move and might reach other fixed point. Or they might reach at infinity, which is the trivial fixed point in this story. In any case, the goal of a theoretician is to understand really the structure of this space, to identify the fixed point and to identify all the topology of these flows. So, who is going to who? How I go from here to there? What is the theory which are behind this fixed point? Okay, and each of these fixed points are represented the mathematical description of the different phenomena we see in nature. Okay? So, the different phenomena, once you identify the symmetry that are behind, each symmetry group has many possible fixed points. Each of them stays for different classes of universality. So, for instance, the easy model stays for the class of universality of spin up and down, so uniaxial, but also for gases and density. Density, in that case, the order parameter is the different density between the gas and the liquid, for instance. Now, it looks very different, but as a matter of fact, they are describing the same class of universality. Okay, so from this idea, in principle, really in principle, one might go integrating this degree of freedom from infinitely large, say from universe, to infinitely small, in principle, of course. So imagine that someone come to you and say, look, this is the Hamiltonian of the world. At that scale, then you integrate one by one the degrees of freedom, and you might swap from certain range to others. Obviously, extremely complicated, but in principle, what one could do. So in a way, you are just peeling the different onions of nature. So there are infinite scale in nature. There is no a definite theory, but there are what is called effective theory. So this is an important concept of the story, which looks the following. At any given scale appear certain degrees of freedom which are relevant, and then you have to look for the Hamilton on these degrees of freedom. And therefore, from this point of view, you really can walk between the universe, going atom, nuclei, go inside the nuclei, and you always discover effective theories like that. And going more and more deeper, you arrive to quarks and so on and so forth. At the end of the day, you arrive to extraordinary conclusions. That if you have a theory with infinite degrees of freedom, which has Lorentz invariants, the theory, as a matter of fact, is a quantum field theory. Full stop. Okay? So from this point of view, you find something extraordinarily deep because you probably know that quantum field theory is the theory used widely for a century to describe the elementary particle processes. So something which occurs at an extraordinary energy scale with process like production, new particle, the Higgs, and so on and so forth,